Again, we recall the definition of vector space. A non-empty set capital V is said to be a vector space over a field capital F if claim 1, V comma plus is an abelian group, and claim 2, for every alpha belongs to F and small v belongs to capital V, there is an element alpha V belongs to capital V such that first condition alpha into U plus V equal to alpha U plus alpha V. Second condition alpha plus beta into U equal to alpha U plus beta U. Third condition alpha into beta U equal to alpha beta into U. Fourth one, 1 into U equal to U. For all alpha beta belongs to capital F and U comma V belongs to capital V. Now we see the next problem. This is similar to this previous problem, that is show that R cross R is a vector space over R under the addition and scalar multiplication defined by the same addition condition but as a minor change in the scalar multiplication. So when we add A comma B plus C comma D in the same manner, add the corresponding elements A plus C comma B plus D. When we scalar multiply alpha into A comma B, the first element always goes 0. Only we operate this alpha with the second ordinate. Okay. So alpha into A comma B is equal to 0 comma alpha B always. So the first ordinate always goes 0. Remember, this is the difference than the previous problem. So only the scalar multiplication, here it is different. So let us see how the problem goes. We need to prove actually here this is not a vector space. Okay, so this is not a vector space. That is show that R cross R is not a vector space over R under the addition and scalar multiplication defined by these two. So in the previous problem we got it is a vector space with respect to this addition, and scalar multiplication is alpha into A comma B is alpha A comma alpha B. Here this is 0. So there is no change in claim 1, because in claim 1 we are just to prove R cross R comma plus is an abelian group. So here with respect to this addition alone we prove abelian group. So there will not be any change in the claim 1. As usual, we prove that this R cross R is closed, associative and commutative as per the previous problem. You can refer. And similarly, we get the additive identity R cross R is 0 comma 0, and additive inverse of any element x1 comma x2 belongs to R cross R is again minus x1 comma minus x2. So therefore, R cross R comma plus is always an abelian group. Now we try to prove the claim 2. So again we consider the definition. The addition definition given us A comma B plus C comma D equal to A plus C comma B plus D, and the scalar multiplication defined as alpha into A comma B equal to 0 comma alpha beta. Now you see, we consider the elements alpha comma beta from R, as well as U as x1 comma x2, V as y1 comma y2 belongs to R cross R. R cross R contains all elements in the ordered pair form. So we consider like this. Now condition A is to prove alpha into U plus V equal to alpha U plus alpha V. So remember, whenever we go for scalar multiplication, we should take care in the first element of the ordered pair. Okay. So here we consider the left hand side alpha into U plus V. Now replace U by x1, x2 and V by y1, y2. Okay. Now we add these two elements. There is no change. Okay. As usual, because the addition condition is same. So we add in the same manner x1 plus y1 comma x2 plus y2. Now we go for scalar multiplication. Now we multiply this alpha inside. So here we need to stick over to this definition. That is, the first element goes 0. Only this alpha gets multiplied with the second ordinate. Okay. So here it is 0 comma alpha into x2 plus y2. So keep this as equation 1. Now look into the right hand side. Our right hand side is alpha u plus alpha v. Consider alpha u plus alpha v. Substitute u and v. That u is x1 comma x2, v is y1 comma y2. Now we make scalar multiplication here. So what happens? This becomes 0. So the first ordinate becomes 0. Second ordinate only we apply alpha into x2. Similarly, when we multiply this alpha with this y1 comma y2, the first ordinate goes 0. Now when we add these two, 0 plus 0 is 0 again. The second ordinate alpha x2 plus alpha y2. Now this is 0. Here we can take alpha as common. So alpha into x2 plus y2. Now we got both the first equation and second equation same. So our first condition is proved. It is true. Okay. Now we go for proving the second condition. Alpha plus beta into u equal to alpha u plus beta u. Again, remember, whenever you go for scalar multiplication, you should take care. Scalar multiplication, you should take care. Okay. So consider the left hand side now. Alpha plus beta into u. Instead of u, substitute x1 comma x2. Now operate this alpha plus beta, this whole scalar with this element. Okay. So again here we get 0 because we are making the scalar multiplication. Then alpha plus beta into x2. The second ordinate exists like this. Now here we check the right hand side, which is alpha u plus beta u. Alpha into x1 comma x2, beta into x1 comma x2. So replace u by x1 x2. Okay. Now we make scalar multiplication. So this is 0 comma alpha into x2 plus beta. Here also we make scalar multiplication. So the first term, this is 0 comma beta x2. Okay. Now add both. So the first ordinate goes 0. Here also it is 0. And alpha x2 plus beta x2 here. Therefore take alpha plus beta into x2. Take x2 common. Now we get the third and fourth equation are same. Okay. So from 3 and 4, alpha plus beta into u equal to alpha u plus beta u. So these two conditions are satisfied. Now we check whether C is true or not. Now to prove alpha into beta u equal to alpha beta into u. So left hand side is alpha into beta u. Alpha into beta into, instead of u, put x1 comma x2. Now we make a scalar multiplication here. So beta into x1, the first ordinate goes 0. Only the second ordinate beta into x2 remains. Again, when we make a scalar multiplication with alpha, the first ordinate goes 0. Second ordinate alpha into beta x2. Okay. And this is 0. Now I associate, because with the same reason, we have alpha, beta, x2 are all real numbers, and r comma dot is an associate, that is abelian group actually. So we can associate. Therefore, we can combine this alpha beta together, then x2. So just change the brackets, alpha beta into x2. Keep this as equation 5. Now consider the right hand side, alpha beta into u. Alpha beta into, instead of u, put x1 comma x2. Now we make scalar multiplication. When we multiply, the first ordinate goes 0. Second one, alpha beta into x2. So look into the two equations, 5 and 6. They are same. Therefore, from 5 and 6, alpha into beta u equal to alpha beta into u. Now, the three conditions satisfied. But we need to prove this is not a vector space. No, this is not a vector space. This only we need to prove. Not a vector space means already climb 1 is satisfied. In climb 2, 3 conditions satisfied. Now we need to check for the fourth condition, which is 1 into u equal to u. Now consider left hand side, 1 into u. So replace u by x1 comma x2. Now this 1 is a scalar. Instead of alpha and beta, 1 is a scalar. So we operate scalar multiplication with this x1 comma x2. So again, the first ordinate goes 0, comma 1 into x2. So this is 0. 1 into x2 is x2. But what is our u? Our u is x1 comma x2. Our u is x1 comma x2. But it is sure that 0 comma x2 is not equal to x1 comma x2. Right? So this is not equal to u. We are getting 1 into u as 0 comma x2. We need to prove 1 into u equal to u. We check, okay? But we are getting 0 comma x2 which is not equal to x1 comma x2. So this 1 into u is not equal to u. Okay. So here the fourth condition is dissatisfied. So we say this 1 into u is not equal to u. Therefore, R cross R is not a vector space under defined addition and scalar multiplication. So in this problem, with a minor change in the scalar multiplication definition, we get the same R cross R is not a vector space over the same field. Okay. So now consider this problem as a homework and do the problem in your classwork note. Now see, here also the same definition. We need to show that this is not a vector space. Again, not a vector space over R under the addition and scalar multiplication defined by the same addition condition a comma b plus c comma d equal to a plus c comma b plus d. See the scalar multiplication alpha into a comma b equal to alpha a. The first ordinate we use the same, but the second ordinate goes 0. So alpha a comma 0. So similar to the previous problem, we need to make the changes wherever necessary. Okay. Solve this problem in the classwork note.